Learning a new programming language demands hundreds of hours of intense, focused effort. You are committing to weeks of late nights, syntax errors, and rigorous debugging just to reach a baseline level of competency. But the actual workload is secondary. The real threat is dedicating all that time to a language that does not align with your specific career goals. If you master the wrong tool, you hit a functional dead end. You spend months studying, only to realize the skills you built cannot be applied to the software or systems you actually want to create. The very first language you choose to learn sets the boundaries of what you can build. It dictates your viable career trajectory from day one. Right now, the global tech industry has a default recommendation, Python. It is the dominant force in the market. The platforms you use every day rely heavily on it. Google, Netflix, and NASA use Python to run their core systems and server-side operations. Tracking Stack Overflow and TIOBE index data over 5 years, Python's growth curve steadily overtakes legacy competitors like Java, C++, and C#. But this peak position creates a dangerous assumption. Universal popularity does not mean it is the perfect tool for every engineering problem. The vital question to answer is not whether Python is a good language. It is whether its specific architectural compromises match the exact system you intend to build. Python is built on a core structural trade-off. It prioritizes developer speed over execution speed. It achieves this by using a highly readable, English-like syntax and relying on dynamic typing. Python is dynamic, automatically assigning variables without manual declarations. Contrast this with C++ and Java, which force manual memory management. This abstraction drops the learning curve, massively accelerating developer speed. However, forcing the machine to manage memory on the fly makes Python inherently slower. Python strictly prioritizes human convenience over machine efficiency. That makes it excellent for rapid iteration, but highly inefficient if you need low-level system performance. Python also uses a specific execution model. It is an interpreted language. Interpreted languages read and execute code sequentially. The machine processes it line by line, in real time. This sequential execution gives you immediate pinpoint error detection. If a bug occurs, the system points out exactly which line broke during the coding process. Compiled languages work differently. They must process and translate the entire block of code before running it at all, which catches major structural errors up front. The interpreted model carries a runtime risk. If a critical error sits on line 100, 99 lines will execute before the program abruptly crashes. This setup makes debugging remarkably frictionless for beginners. But it also introduces runtime vulnerabilities that strict legacy enterprise environments actively try to avoid. Python's most significant competitive advantage is not the language itself, it is the massive standard library and third-party ecosystem built around it. Look at this effort versus impact quadrant chart. Python sits firmly in the top left quadrant. Low setup effort, high capability. It earns this spot through pre-built frameworks. You pull in Django for web or TensorFlow for AI, entirely bypassing months of foundational coding. This library shortcut allows small teams, or even solo developers, to rapidly build and deploy enterprise-level machine learning models and complex data analytics. The trade-off for taking the shortcut is dependency. You rely heavily on third-party frameworks to function, rather than understanding or writing the foundational logic yourself. And there is a hard edge case limitation. If you are building highly complex Internet of Things devices or working with resource-constrained electronic circuits, the strictness of C or C++ remains the required industry standard over tools like MicroPython. Python's true power lies in assembling highly capable pre-existing structural blocks. It gives you a massive return in capability for a minimal time investment. To successfully leverage Python, map its architectural strengths directly to your specific career trajectory. This decision tree starts with one question: what is your primary goal? If you are an absolute beginner or time-poor learner, the answer is a definitive yes to Python. It gives you immediate momentum. You can build functional applications quickly, though you will eventually need to learn HTML, CSS, and JavaScript if you want to move into full-stack web development. If your goal is to switch careers into data science or artificial intelligence, Python is mandatory. The language is uniquely intertwined with these booming sectors. But be prepared. You must master complex mathematical libraries like NumPy and PyTorch alongside the core language itself. Finally, if you are targeting system-level architecture, game engines, or hardware, The answer is to avoid Python. You should use C++ or Java. Pragmatic developers who are building resource-heavy desktop gaming engines, low-level operating systems, or strict legacy enterprise software cannot use Python. The execution speed limitations and reliance on interpretation make it the wrong tool for the job. Python is the ultimate strategic tool for rapid, high-level technological impact, provided you respect its structural boundaries and target the correct industry sectors.